Dr. Gallman. Today I'll be covering Lab 3 in Physics 2211 on the topic of black holes. To introduce this lab, the purpose is to find the mass of a black hole by analyzing a star's orbit. After this, the goal is to find the initial velocity a ship must have when leaving the surface of the planet to fly around the black hole without crashing into the black hole or into the planet, using the calculated mass of the black hole from Part 1. The overall lab results state that the calculated mass of the black hole is 1.30692 times 10 to the 34th kilograms, and the initial velocity of the ship needed to avoid crashing is negative 1.7438 times 10 to the 7th meters per second in the x direction, and 7.9659 times 10 to the 6th meters per second in the y direction. A fundamental physical principle used throughout this lab is Newton's second law of motion. Newton's second law of motion, the momentum principle, states that the rate of change in momentum is directly proportional to the net force exerted on a system. In other words, the net force is equal to the product of the mass of a system and its velocity. The net force can be broken into the parallel and perpendicular components, where the perpendicular net force component is the change in direction perpendicular to the parallel net force, which is equal to mass times velocity squared over the distance times n hat, and the parallel component of the net force is the motion of an object, which is equal to the change in the magnitude of momentum over a change in time times p hat. From Newton's second law, we can derive it to achieve the velocity update formula, which is used to find the velocity of an object after a time period. Related to the velocity update formula is the position update formula, which is used to find the new position of an object after a time period has passed. Another important formula used in this lab is the magnitude of the universal gravitational formula, using the gravitational constant g, which is equal to 6.7 times 10 to the negative 11th. For the experimental setup, the system is defined as the black hole and the surroundings as a star. For the initial conditions of the experiment, the mass of the star was given as 2 times 10 to the 30th kilograms. The change in time, or delta t, is 86,400 seconds, which is equal to 1 day, and the gravitational constant as identified on the last slide. We apply Newton's second law to find the gravity, so we find F net, and then we find the parallel component of the net force by finding p hat, and then the change in magnitude of the momentum divided by delta t. Then we find the perpendicular component by subtracting the parallel force from the net force, and then we use this information to find the mass of the black hole. Here is a recording of the simulation. And while this is playing, I will say I found the mass of the black hole to be equal to 1.30692 times 10 to the 34th kilograms, the magnitude of the net force to be 8.4695 times 10 to the 28th newtons, the magnitude of the parallel component as 3.645 times 10 to the 27th newtons, and the magnitude of the perpendicular net force is 8.463 times 10 to the 28th newtons. Now I use the mass of the black hole in Part 1 for the setup of Part 2. The system is a spaceship, and the surroundings are the planet and the black hole. And this equation is used to find the speed of the planet, and this equation is used to find the velocity of the planet. Perfect. So to calculate the net force, we need to first find the net force of the black hole on the planet, then the net force of the ship on the planet. And after you find both of these, sum them together to get the net force on the planet, the total net force on the planet. So first you need to find r, and then find r hat after, and then plug it into the universal gravitational formula right here, g times big M times little m over r squared times r hat. And after this, we need to apply the velocity update and position update formulas to make the planet and spaceship move. And I found that the initial velocity of the spaceship needs to be negative 1.74 times 10 to the 7th meters per second in the x direction, and 7.9659 times 10 to the 6th in the y direction. And the closest distance between the ship and black hole was 1.8246 times 10 to the 10th meters. Possible sources of error include that I could have ran the program for a longer time to achieve a more accurate mass, and also I could have chosen an incorrect initial velocity because I used the guess and check method to find this initial velocity. And finally, the time interval for the initial velocity trial could have been too short. So the net force parallel and perpendicular components are the same as the rate of change of momentum and its parallel and perpendicular components, since the net force is equal to the rate of change of momentum over the change in time. However, it is easier to find the change in momentum than to find the net force. So, what if I wanted to orbit the black hole? In order to orbit the black hole, the ship should have a similar velocity to that of the planet, but the y component must be slightly larger, and the x component should be negative and smaller to avoid collision with the planet. I used the guess and check method with this situation and found that the ship's initial velocity would be negative 2.8 times 10 to the 6 in the x direction and 7 times 10 to the 6 in the y direction, with the planet's orbital velocity being 7.037 meters per second. 7.037 times 10 to the 6 meters per second. Thank you.